Hi everybody, welcome to the Points of Topology NPTEL Part 2 PS22 course. My name is Shavik and this is the first live session. So I'm working in electronics costume and Madras, and this course will have total 12 live sessions, but I plan to take one more summer sessions. Okay, so there will be total 13 interaction between us. So the target of the session was to basically solving problems, clearing doubts, the assignments which has already been submitted, those things, clearing doubts, all these things are basically the target of this session. Okay, so basically we in this kind of session we shall mainly focus on problem solving, doubt clearing, all these things. So please try to make use of these sessions. Okay, so so how many students has joined? So it's the time was 6 and now it is 6:06. So okay, so there is one student, Mr. Mustaq. Mustaq, can you please unmute yourself and let me know that in which that you
Yes,
are.
screen visible and you are audible too.
Okay, thank you, Mustaq. Thank you. Okay, since the first class, so I must know the from what is your background. I mean, you are studying graduation or post graduation. What is your status? Can you please let me know?
Graduation.
Okay, got it. Okay, so let's wait for a couple of minutes or else we can start. So since you are the only student that attended this course, so can you please tell me whether you take this topology course previously in your graduation, or is this the first instance you were looking at this topology course? Please let me know whether is this your first topology course or you have done this topology course previously in the graduation. Okay, since it's the first course, problem, we are here to deal with this. Okay, so it's a points topology part two. Is it right? Let me check on part one. Okay, so so it's already now 6:10. So let's start the live session. Okay, so if the student come later on, then we can again start. No problem. Oh, so this is a basically a course on points of topology part two. So this course consists of basically the following chapters. So the first chapter is compactness. Second chapter is connectedness. Third chapter is um, separation axioms. Fourth chapter is countability axiom. Fifth chapter is dimension. Sixth chapter is topological groups. Seventh chapter is manifolds. So more or less these are the all, so these are the all things which we must learn in this points topology part 2 course. Okay. Okay. So Mustaq, can you please confirm whether you took this points topology course in your graduation, or this is the first instance in which you are dealing with this course? Mustaq, can you please confirm whether um, this is the first instance with which you are dealing with this course? Okay, so it seems it's the first instance. So let me start from the basics. Okay, so we shall start from compactness. So from today onwards, first let's take on there is something called compactness. Okay, so first a point is that, so many of you have done so okay. So Mustaq, I hope you have gone through the matrix space course, and there you have seen something called compactness. Not only that, in the course of real analysis, there is also something called compactness, right? And hopefully you have gone through that. So the thing is, the compactness basically fundamentally is that whether you some set can be placed inside a ball or not. That means we have some set, but it's a finite, so we can take put it inside some ball, correct? So it says, so it's a finite, so it's like compact set. However, suppose we have some line like this. Okay, so of course we cannot, I mean, and it goes to the infinity. So so it doesn't matter how big ball we consider, we cannot put this ball inside this thing, correct? So that's why the second example, this line is not compact, but this star is of course compact, correct? All right, so this is the thing. So that's what the fundamental target of compactness, that means that is that means whether something is closed enough or not. So that's what by compactness we always deal with, understand? So this is what the compactness means. Is it clear? So yeah, so that's what it is. So so the thing is, Yeah, so the definition of compactness. Okay, so there is nothing much to explain. So method. So the thing is that in the case of real analysis, you have I assume that you have you know the definition of compactness. There, what you have, so you have seen that suppose you have some um, a set subset of some of the included space R is said to be compact. If any open cover, if any, if that if any open cover is a finite subcover, correct? So that's what the compactness means, right? The same definition holds the metric space. That is, if your metric space x tau, let me write it down. So suppose we have some metric space x tau, then x is said to be compact. Then x is also said to be compact if every open cover has finite subcover. Correct. So this is a definition. The same definition topology also. That is every open cover finite subcover. So let me write it down to definition in a formal mathematical notation. So x tau be a topological space. So x tau be a topological space. Okay. Then x is said to be compact if every open cover has finite subcover. Correct. If every open cover is a finite subcover, that is what the topological space means. Sorry, that is what the compactness means. That means what? That means if we take any open cover u alpha with some indexing alpha, this is open cover, then there exists alpha 1, alpha 2, alpha n such that x can be written as union of u alpha I. Okay. So this is what by we mean the compactness. Okay. So there is so that's a definition, formal definition. However, the definition is there, but the reality is different, right? So for that, what do we need to do? So for example, consider the real line R. Is it compact? The real line R, is it compact? Please do calculate it. Please do figure out. That means what? Either you need to find that, show that any open cover has a finite subcover, or you have to show that there exists at least one open cover which does not exist a finite subcover, right? In any ways. So please try to do it by yourself. Take your time. Okay, so basically let me give the hint. So basically the hint is that It is not compact. It is not compact. Owen. It is not compact. Okay. So basically, construct an example for that. Okay. So basically, you need to find an open cover which does not admit a countable subcover. Sorry, finite subcover. So that's what you show. So please take your time, think about it, let me know. I shall be back within few minutes. Hmm. So, Mustaq, are you able to figure out why it's not compact? Do you have any idea? Or are you able to produce any open cover which does not have finite subcover? So, what is the target? Target is to create an open cover which does not have a finite subcover, right? That's a fundamental target to show something is not compact, correct? So, what is one possible way? So, basically, here I am creating an open cover which does not have finite subcover, okay? So, take the open cover U. Open cover the form minus n comma n. So, this is an open cover of R, correct? So, now, of course, so how this looks like? So, we have open cover R and we have in between point 0, 1, sorry, minus 1, all this. And in between open cover the form minus 2 plus 1 minus 2 to plus 2 dot dot dot, correct? However, however, this open cover, but this open cover does not have finite subcover. Why? Suppose, so let's assume, suppose it has finite subcover, correct? So there a finite subcover. That means, so that means what? That means there exist integers n1 to nk such that R quantity was union of minus ni to ni I is equal to 1 to n, correct? Right. So without loss of generality, we may assume that, assume n1 is equal to max of n1 into n. Then this implies what? This implies R equal to, So r equal to minus into plus. But of course, this is contradiction, correct? So this implies what? This implies r is not compact. So this is the target, correct? So Musa, please let me know whether is it clear or not. Okay, so Mustafa, I hope this argument is clear. So the next prop, so the next um, thing is that, so well, 1 minute. Let me just open the compactness chapter for the next prop. So there is a one theorem which tells that this theorem tells that that closed subspace of compact space is compact. Closed subspace compact space compact. So okay, Musa, please try to prove it. So basically, what we need to show? Suppose y subset of x and suppose x is compact. We need to show that y is compact. So what to do? We need to start an open cover and we need to show this open cover with a fire subcover. Correct. So that's what we need to show. So just please to try to. That means what? From creating an open cover of y, we have to go to an open cover of x, and then we need to use the fact that x is compact. That means we have final open cover, and from that we need to get back into y by removing some extra portion. So please try to do it by yourself. Take your time. Okay, Mustaq, are you able to figure out that how to show that closed as a compact is a compact? Okay, so let me write an outline for you. Just hold on. Okay, so what we should start. So we should start with like, so suppose you be an open cover of y, correct? Since u is an open cover of y and y is closed, so u union x minus y, this forms an open cover of x, correct? Now given the fact that x is compact, that means any open cover of x has a finite subcover, correct? So we can now use that. So that means this open cover u union x minus y, this also have finite subcover. Okay, so so let u1 u2 un union x minus y, this covers x. So this implies what? This whole portion u1 to un, this covers y, and this implies what? That open cover u has a finite subcover, namely u1 u2 un, correct? So this is the argument. So is this argument clear to the students? Well, there is one more student joined. So there is one more student joined, possibly maybe a few minutes ago. Can you please unmute yourself? Please let me know your background. So Rahul Kumar, can you please unmute yourself and let me know your background?
Hello, sir.
Hi Rahul. So
Sir,
yeah, continue please.
I was from Central University of Jharkhand. I was just doing this course to learn some skills on spaces, Banach spaces.
I see, I see. So you are a faculty or a student, right? A student, is it?
I'm just a student, sir.
Okay, okay. So currently you are in graduation or post graduation?
Post graduation.
Okay, just hold. Video got freezes. Just hold. Okay. So can you please tell me whether this course you took previously or this is the first time you are taking this points topology part 2 course?
This is my first time. And I was watching this lecture,
Hmm.
but I'm not understanding because I didn't saw the points at topology part one.
Okay, forget about that. I mean, I am just asking that in the university or college, in the university, was there any course on topology?
In my second semester, I have read topology,
Hmm.
so I am familiar with topology.
Okay, okay. So in that courses, can you please roughly tell what are the things you have learned, if you can remember at all?
Subspace topology, product topology, order topology, and compactness
Hmm.
and Urgion's lemma I studied in that course,
Okay, okay.
and compactness also.
I see, I see. Perfect.
Just a basic topology, nothing
Hmm. Understood.
much deeper.
Okay. So did you solve problems of any textbook or only theories?
Whatever the teachers gave me in the classroom, just I only wrote this in notebook and try to attempt again myself. Nothing not much extra.
No, no, I understand that, but my point is that, so have you only learned the theories or did you solve problems also?
No, I don't able to solve the keep up with the problem.
Hmm, got it. So, okay, so the point is that this course, this points topology part course, this live sessions are only mostly for problems and small theories. Okay, so in this course
Okay,
we will see a lots of problem solving. Okay,
okay, sir.
however, initially you started something Banach space, right?
Yes, sir.
So, okay, so when okay, so Banach space we will see, but later on because it is not directly in the part of the topology. It is part of the functional analysis. I hope you know that.
Yes.
And so we'll see the Banach space later on. Right now we shall concentrate only in uh, topology portion.
Okay, sir.
So which book you have followed in the university?
Mm, Let me check. They gave me introduction to topology. I don't know the writer name, but they told me to follow the Munkrens. So I read the Munkrens, but I'm not able to solve the problems of the Munkrens.
Okay, that will not be a big problem because here we will see the problem solving. But for that, can you please tell me whether so like points topology in the product topology, subspace topology, all those basic things. Did you solve any kind of problem that also, or only theory portions?
I just do only theory person.
Got it. Understood. And this part two course you have not taken previously last semester, right? Part one course.
Yes, yes, sir.
Okay. Okay. So tell me one thing. Do you have that class notes of the Professor Sastri?
Repeat. Can you please?
Yeah, Professor Sastri has some class notes. Do you have that?
Yes, yes. NPTL
Yes.
in NPTL. Yes,
Correct.
I have that one.
So have you tried to follow those notes?
Yes, I am watching this video.
No, no, not
So
video.
that
Just asking the lecture notes, not you.
lecture note, I didn't read that because I'm enrolled few days before.
Okay. If you don't have the lecture note, you please email to NPTEL team. They will send you the lecture notes. Okay. The point is that if you depend on the videos, then it will be. I mean, come on, videos have been recorded many years ago. So you should go through the lecture notes because lecture notes are frequently updated actually.
Okay, sir.
Then after going through a lecture note, you watch the video. But if you first watch the video, then lecture note, it will be very difficult to understand the subject itself.
Okay, sir.
Okay. Yeah.
Thank you, sir.
Yeah. So right now there is some one problem which tells that closed subspace of compact space is compact. So did you understand the proof? Please let me know. Or if not, then please also ask me. I will again re-explain.
Sir, I know the statement, and I my teacher tried to help me to solve this,
Yes, yes, yes.
but here I am joined late, so I didn't understand what
Ha
is
ha.
the.
Okay, okay. No problem. No problem. No problem. So in this problem, what we are doing? What? Hold on. So in this problem, basically what we're doing is that we're trying to show the closed subspace of compact space is compact. Okay. So for that, what how to start? We need to start with the y, which is a closed subspace of a space x, and x is compact. And we need to show what? We need to show y is compact. Correct?
Okay, sir.
So in order to show compactness, what we need to do? We need to start with some open cover, right? And we need to
Hmm.
show that open cover admits a finite subcover. You that must you know, right?
Yes, sir.
Yeah. Now, if you take an open cover u of y, then if you take the union of the open cover with x minus y with the y complement basically. Now, since y is closed, so x minus y is open.
Hmm. Yes.
So union x minus y, this is again an open cover of whole of x, correct? Now
Yes.
x is given to be compact. That means what? This u union x minus y, this will contain a finite subcover. So there is u1 into un such that this u1 into un union x minus y, this covers x. So this means what? This u1 into un, this covers y. So this is the argument.
Yes.
So is the argument clear to you?
Yes, sir.
Okay.
This means the U1, U2 is the open cover of compact space Y.
Correct, correct. Then that I understand. But in between the arguments are clear.
Yes, sir.
Okay. Okay. So can you please tell me that the set of real numbers are okay?
Hmm.
Is it compact?
No, it is not compact because it is not bounded.
Okay. Apart from bounded, can you show? Can you construct an open cover which does not have a finite subcover?
We can construct open cover just using the mm, cardinality n comma n
In
minus n comma n
okay.
union.
Minus n comma n. Correct. Very good.
This is the open cover for R.
Correct. Correct. Right. Absolutely correct. Okay. Now, can you tell me? Do you know cofinite topology, co-countable topology, these things? Or have you heard about this previously?
Yes, cofinite topology it means the complement is finite and co-countable means complement is countable. So
Correct,
every countable set is closed and every finite set is closed in that topology.
correct. So the next question is, if X tau be a cofinite space, then show that X is compact. That means in the cofinite topological space is always compact. That's what you need to show. Okay. So that means this space has a property that any I mean any set if it is open that its complement is finite and vice versa, right? Now please try to show whether it's compact. That means you need to start with an open cover, call it U alpha, and you need to show that it admits a finite subcover, correct? So take your time. Please try to do it by yourself first, or else I will explain. Okay. So please try to do it by yourself. I shall get back. I shall get back after a few moments. So Rahul, can you please explain that if the space is cofinite, then how the it will be compact?
Sir, we need to find a open cover for X,
Mhm.
which cover the which cover X.
No, no. In order to show something is compact, what we need to show? We need to show that any open cover will admit a finite subcover. Correct? Any open cover, right?
Yes, sir.
Yes. So for that, what we need to do?
We need to construct open cover.
No, no. That's what. No, no, no. See, in order to show, we need that something is compact. What we need to show? We need to show that any open cover. It is any, right?
Yes, sir.
So there is nothing to there is nothing to construct. To you have some arbitrary open cover and to show that will admit a finite subcover, correct?
Okay.
So do you have any idea how to proceed this kind of problem?
We can take as like U1 is just one element removing from X and U2 is removing two elements from X.
uh, no, no, that's okay, but no, no, I mean, no, no, I mean, are you giving some specific open cover? Is it like that?
Yes, 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 sir.
That's what I'm trying to explain now, that it is not a space. You have to show that any open cover, you cannot choose something specific, right?
Sir, I am taking U1 as X minus X1
No, no,
and U2 equal to X minus X1 X2 is this type.
but this is a particular open cover, correct?
Okay, sir. So we can't take this one.
We can't take anything. You have to show any open cover. Any open cover you have to show. You cannot choose particular one, right? When you can choose particular one, when you need to show something is not compact, that means you have to choose open cover which does not have a finite subcover. But here what we need to show? You need to show X is compact. That means you have to choose any open, I mean, you have to show any open cover admits the finite subcover, right?
Yes, sir.
So do you have any idea how to process this kind of problem?
No, sir.
Okay, so let me explain. So let U be any open cover, okay? Okay. So we need to show that U admits a finite subcode. That is what we need to show, correct? So,
Yes, sir.
so, so the collection U contains the elements of the form U alpha for some index at alpha. Okay. Now choose some alpha and fix it, and consider the corresponding open cover U alpha naught. Open set U alpha naught. Now U alpha naught is open. This implies what? X minus U alpha naught is a finite. Correct?
Yes, sir.
So this contains the element. So since it's finite set, so we can assume that it elements are x1, x2, xn, right? It's a finite set, correct? Now since this collection U alpha is an open cover, so the elements xi must belongs to U alpha I for some alpha I, correct? And that means what? That means x equals to nothing but U alpha naught union U alpha 1 or union U alpha n. So this is the argument. So tell me where is the doubt you have?
Sir, can you could you please explain me where you change the pen color in that line?
Oh, huh. So we choose some index alpha naught and fix
Yes, sir.
it. Okay. And so we have the
Yes, sir.
corresponding U alpha naught. Now U alpha naught is an open set, correct?
Yes,
And our space is a cofinite topology, right? So X
yes.
minus U alpha naught is a finite set, correct?
It, it means U alpha naught is uncountable set. Maybe countable,
Maybe countable, maybe uncountable.
but X minus U alpha naught is finite.
Yes,
Yes,
correct.
sir. I
Now,
understood.
then rest of the argument did you understand?
Yes, sir. I
Okay.
understood.
So the whole argument is clear, is it correct?
Yes.
Okay. Okay, take your time and think about it if you understand properly or not, and let me know. Then only I will start the next problem. Okay, please take your time.
Sir, how we can say this construct a finite cover,
Hmm. So,
because we are taking the index. The index is the countably infinite maybe, no? So how can we say finite subcover?
correct. However, we have this x 1 minute. We have this x1, x2, and xn, correct?
Yes, sir.
And U alpha, I mean the collection U alpha, it's an open cover of X, correct?
Yes, U alpha open cover. But this is the question now. How can we say? If, oh, okay, sir. No, I understood.
Hmm. So please
Understood.
go through that one once again and let me know if you have any doubt. Is it clear? I mean,
Okay, sir.
yes. Please take your time and let me know whether you have any doubt. No, no hurry. Okay.
I understood, sir.
Okay. So can we go to next problem,
Sir, sir.
or you may spend more time on this. We will wait. No problem.
So we can move.
Okay. So the next problem is that. So you know the co-countable topology, right? You told.
Yes.
So one minute, what is that? So let x tau be a co-countable space. Show that x is not compact. So in a co-countable space, you have to show that x is not compact. Okay.
Sir, as like the previous one, we are not able to find the finite subcover because this is the countable.
No, no. That means for this problem, what you need to do for this problem, you have to show that, or you have to choose some particular open cover which does not admit a finite subcover. Is the difference clear from the first problem?
Yes, sir.
So for this problem, you have to find out some open cover which does
Which is
not
not.
admit a finite subcover. Correct.
Okay, sir.
So please try to construct an open cover. So please think and let me know.
So we took x minus x1 x2 dash 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 all the cover like this. U alpha
Okay.
equal to x minus x1 x2 dot 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 like this.
Okay. So u alpha is equal to,
X minus x1 x2 x dot 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 x3.
so u alpha is equal to x minus x1 x2 x3 dot dot dot. So this is one open set. Then
So again y1 y2.
tell me then next.
U alpha 2 is x minus x2 x3 x, we remove x1 and we took x2 x3 and so on. In the similar way, we are not able to get a finite
So why will not be able to get finite something?
because it is countable. X may be uncountable set, so we are not able to get a
Hmm.
finite subcover.
No, no, what the countable argument comes here. So you want, I mean, uh, x can be countable also, right?
Yes, X can be countable, but we are not able to get a finite subcover. For compactness, we need to finite subcover.
But each u alpha 1, u alpha 2, all this u alpha and all these things are each u alpha is countable, right?
Yes, each U alpha is countable
So that's what, so why we cannot have finite of them to cover the whole of x?
because X can be infinite.
X is already infinite. There is no doubt about it. X is already infinite, right? Because that's why we are saying now that x minus u is countable set, correct? So x is already infinite, right?
So
So why we cannot get finite u alpha i's to cover whole of x? So instead of finiteness, so suppose you can, for simplicity to understand, you can take, there are already only u alpha 1, u alpha 2, u alpha 3 which covers whole of x. Suppose you assume that, correct? Okay.
yes,
That means what? Their union u alpha 1, u alpha 2, u alpha 3, that be whole of x, correct?
yes.
So now tell me what is the union of u alpha 1, u alpha 2, u alpha 3?
Union U alpha one to if we took the finite union, we included one to x1 to xn, but we are excluded xn to xn to xn plus one xn plus two. These all are excluded in the union. We are not able to get the complete whole x if we took the finite union.
So suppose if you consider u alpha 1, u alpha 2, u alpha 3, then what will be this union u alpha 2, union u alpha 3? Tell me. So it will be what? X minus
x minus
x minus
x3, x4, and so on.
x3, x4, and so on. Correct. So that means if we have u alpha 1, that means what? If we have u alpha 1 dot u alpha n, so their union will be what? Their union will be x minus
xn minus x.
xn plus 1 and dot dot dot. Correct.
Yes, sir.
That is why any kind of finite union cannot cover the whole of x, right?
Yes, sir.
Is the argument clear?
Yes, sir.
Okay. So do you know what does the Hausdorffness mean?
I know the definition of Hausdorff. Mm,
Yes, yes, tell me.
The 2 point in tau in X, then every open neighborhood of both components are disjoint. Open if A and B belong to X and open neighborhood of X, A and open neighborhood of B are disjoint.
So does this happen for all open neighborhood or does this happen for certain open neighborhood?
Every neighborhood of A and B.
See, I mean, open set, the whole space is an open set, correct?
Yes, sir.
Then any point belongs to the whole space, correct?
Yes,
So that means any open neighborhood cannot have empty intersection, right?
yes, sir.
So that means what?
But we may there exist open
Yes,
neighborhood.
correct. There exist open neighborhoods such that their intersection is empty.
Yes.
Okay, so the next question is that not a question, it's basically a theorem, but it's a question also. Uh, every compact space, every compact Hausdorff space is closed. So this question is you need to show that any compact Hausdorff space must be closed. Sorry, I mean let me write any compact subspace of Hausdorff space must be closed. Any compact subspace of Hausdorff space must be closed. Okay.
Yes, sir.
So, so can you please try to prove that? Basically, what you need to show? You need to show that suppose A be a compact subset of X, then you need to show that X minus A is open. Correct. So please try to think at least. Take your time.
Sir, can we take the two different point, which one belongs to X and other belongs to the subspace,
Mm,
and we took the neighborhood of that point separately
hmm.
from that side? Can we say anything about this?
Yes, yes, yes. Please go. Please start the argument. Yes, please start the argument.
Mm, a subspace A,
Hmm.
subset of, subspace A of X, and A is compact, and we took the an element A which belongs to A, then there exists an open neighborhood of that point X, and we took the another element Y in X, and there exists an open neighborhood of Y. As a as the space is host of, then we get the distinct neighborhood,
Okay.
and their intersection is empty.
So, but we need to show what? We need to show that. We need to show what? We need to show that.
A is closed. We have to show
It.
A is closed.
That means, in other words, x minus a is open. Correct.
Yes,
That means if we take a, we need to show if we take any point y from x minus a, then there exists a neighborhood u such that y belongs to u, which lies entirely in x minus a. Correct. This is what we need to show. Correct.
can you please explain the last line?
I mean, if I mean, we need to show x minus a is open. Correct.
Yes, sir.
So that means what? If we choose any point in x minus a, we'll get a neighborhood u such that y belongs to u, which lies entirely inside x minus a.
Yes, sir. Understood.
Right. So that's what we need to show. But the argument that you gave, only we have u intersection b is equal to empty. But we must have u intersection a is equal to empty. Correct. Then only we can say u subset of x minus a. Correct.
Yes.
Yes. Please try to attempt it another way.
Sir, I am not getting anything.
Hmm. Okay. Let me see. Just hold on. Okay. The argument is as follows. So choose y belongs to x minus a. Okay. So this is our x and this is our a. Okay. And we have some point y lies outside in a. Okay. So that means, so now for each a, since of course since y belongs, does not, y outside of a, so if we took any a belongs to a, so of course y will not equal to a, right?
Yes, sir.
So by property of Hausdorffness, we what will get? There exists a neighborhood y of y and a neighborhood vy of a such that uy intersection vy empty. Is it correct?
Yes, sir.
So we are getting uy here and we are getting vy around some here. Okay.
Yes.
So ideally we ideally want, let me just change the notations. So we are getting this open neighborhoods UAVM for each of the A, right? Okay.
Yes.
Now consider the open cover PA which belongs to A. Now this open cover VS we are getting for each A belongs to A, correct? So if we take all those VS, then this VA will create an open cover of A. Is it clear?
Yes, sir. As A is compact.
No, no, no. Compact we have not even used at this point, right? See,
So we
for
getting a open cover because we have A is compact. That's
no,
why
no, no,
we are
no,
getting the.
no, 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 no. Compactness give only open cover. Will have finite subcover, but here we are constructing an open cover, right? How we are getting open cover? So
Okay,
first tell me
so
the what is the definition of open cover?
let's say
First tell me what is the definition of open cover?
open cover. Let's say
Yes, tell me what is the definition of open cover?
I don't remember. It's a,
No, no, I mean math. I mean precise statement you might not remember, but what is the definition? That much you tell, isn't it?
open cover.
Open cover means open cover space is a collection of open sets which covers whole of X. That means we have some U alphas such that X equal to union of U alpha. So this covers whole of X. So this U alpha is called an open cover.
Okay, sir.
Then I mean without understanding the open cover, how you understood the compactness?
I just forget the definition.
No. Now tell me what does it mean by finite subcover?
Finite subcover. The collection of open cover and collection of finite open cover which cover X.
Finite collection of finite open cover which cover?
X.
Okay. See, I mean, you should not forget definition. Without definition, you will not understand what is even going on, right? If
Okay,
you
sir.
can't remember definition, you should tell the first place, right? Without just, I mean, the point is you can't you can't keep on mugging up, right? That will not work in science, even, right? You have to
Okay, sir.
remember the definition. Okay. So first, tell me, is it clear to you whether V of A is open cover of A? This line is clear to you or not? First, tell me that.
Yes, sir. Clear, sir.
Why? Why it is an open
Sir,
cover?
sir, because every point of A we get a open set.
Correct only. So that means we are one. So that means for each A we are getting open set which covers A, correct? So
Yes,
that
sir.
means what? So now, okay. So now A is given to be compact, correct?
Yes, sir.
So that means this open cover admits a finite subcover. Is it clear?
Yes, sir.
Okay. Now, no sooner the fact that this open cover admits finite subcover. So we can write it like VA1, VA2, VAN. Okay, this is the finite subcover. Is it clear?
Yes, sir.
Okay. Now remember that each of the points AI, where each A1, A2, AN, this all lies inside A. Okay. Now remember that each of the point AI, for each of the point AI, we will have some Uy such that Uy intersection VAI is equal to empty and Uy contains Y. Can you remember that?
Yes, sir.
Correct. So that means what we are getting at this situation is the following. We have some X, we have some A, we have some point little y, and for each point A in A, we are getting an open set. Sorry, it should be U of A. For each point A in A, we are getting open set containing A, which is known as VA, and open set containing Y, which is UY, correct? And for each point, we are getting things like that. Okay. So now can you please create an open cover which lies outside A of M but contains X? Can you please do that from the picture itself?
So we need to construct a open cover for A, which
No, no,
which contain element Y.
open cover has already been covered or constructed, and we got a subcover which we have denoted by VA1, VA2,
VAI.
VAN, right?
Yes.
So we already have an finite subcover of A. And for each of this element of VAI, where we already have some UAI which has disjoint, and UAI contains each Y. So now the question is, given this information, can you construct an open set of Y, open set containing a Y, which lies outside of capital X? Think about it.
We took the intersection of the with the every open cover of A.
Every open cover of A, you saying that we must take the intersection.
Yes, sir. That is the lie outside the A.
Intersection of
No, 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 no.
I know. Of course, so we have to go outside of A. We cannot take
Yeah,
the intersection, right?
intersection.
So tell me what the obvious task to do here.
We just removed the neighborhood. We took the neighborhood of Y and minus U intersection of UI. UIs.
Sorry, repeat again.
We take a neighborhood of Y
Yes. We
and subtract.
we already have neighborhoods
Yes,
of Y, right?
and subtract it from the intersection of cover of A. UAI, VAIs.
But we already have some neighborhood UAI around Y for each AI, correct?
Yes.
So use these things to create an open set around Y, which lies entirely outside of capital A. Just look at the picture, think about it. take your time. I shall back in a few minutes.
So if we took the V, capital V equal to V A1 intersection V A2 intersection that is V intersection V AN, and we took the open neighborhood of Y which does not intersect with these, which does not intersect with this capital V, then we get a subset which does not intersect with A.
So you are considering the taking the intersection of VAIs, right?
Yes, sir.
But that in the that intersection itself lies within A, right?
Yes.
So how you
And
can, yes, yes, continue.
and we taking the in open open a open set which contain Y and lie outside A
So
completely.
that's what the we need to show how you're considering an open set lies outside. That's it, the question, right? I mean, I'm not understanding the point. I mean, we need to create
So
or
as X is housed off,
yes, yes.
that's why we get um, open neighborhood distinct from
Aha,
the.
UAI containing Y and VAI for containing each point of little a. Correct. Then,
So from that case, we are able to construct a open neighborhood of Y which do not intersect with the
ha, yes,
this
yes.
capital.
What is the open neighborhood? What is that neighborhood? That's what I'm asking.
For of Y.
Yes, of course.
Y mm, X minus intersection of these capital V.
The capital V lies within
Mm,
capital.
X minus this capital V. Yes.
I mean,
X minus capital V.
ha,
This
but
is the
X minus capital V. But it will be a closed set, right? X minus capital V will be a closed set, correct?
X minus capital V is closed.
Because Vi is open, so X minus capital V is closed, right? Isn't it?
So we need to so X minus Vi is open.
No, no, that cannot happen. I mean, Vi given to be open already. Vi is known to be open, so X minus Vi is closed, right? Because the complement of open set, right?
Yes, sir.
Correct. So the thing is, see, for each point A, we are getting an open set UA containing Y, and we are getting intersection VS containing A. Correct.
Yes,
So
sir.
we can take V to be all this union of VAIs, and this contains capital A, of course, and U to be intersection of all these UAIs. Okay. Now each UAI contain Y. So this intersection U contains Y. Is it clear? Because the U because we are getting UI around this point Y, right?
Yes, sir.
So we are taking their intersection. So all the intersection will contain y, right?
Yes, sir.
And here we are taking the union of all possible v's. So it will be full of x. I mean, it will contain here also, right? Correct.
Yes. Yes, sir.
Yes. And of course, from this diagram itself, u intersection v empty. Is it clear?
Yes, yes, sir.
Okay, so please try to show that u intersection v is empty mathematically, not diagram wise.
What, sir?
Try to show that u intersection v is empty mathematically. That means you have to assume that suppose u intersection v is non-empty, then you have to find some contradiction, correct? So please
Yes,
try
sir.
to, yes, please try to do that. So please take your time.
Sir, if x belong करेगा u intersection v,
Mhm.
v then this implies x belong to u and x belongs to v. This implies there exists an open set ux with subset of x, and there exists an open set vx with subset of v.
Okay.
Yes, and the space is Hausdorff.
Okay.
So so there does not exist two disjoint open set which contain both, which contain
Okay.
x.
Hausdorff means there exists two open neighborhood which have empty intersection, right? But it does not
Yes.
mean that any open neighborhood, neighborhood has an empty intersection. That cannot be possible, right?
So we are able to find ux and vx
Yes.
with subset of u and subset of v. As x is Hausdorff, then we how we say there exist two neighborhood of.
But what is the contradiction? That's what I am unable to understand. You are saying we are getting x belongs to ux and x belongs to vx subset of v. Correct. Okay, then.
As x is Hausdorff, we are getting two distinct subspace
Hmm.
for x.
But that can be possible, right? What is the definition of Hausdorff? Definition Hausdorff tells that if we have two distinct point, then we will get two distinct neighborhood which are disjoint. But here you are saying for what is saying now? No, no. I mean, but what is the contradiction? You have assumed that x belongs to u intersection v, correct? And from that you explain that x belongs to ux and x belongs to vx. But what is the contradiction? Can you please repeat? I am unable to understand.
I am telling that ki,
Hmm.
that x there exist two x is Haus as x is complete x is Hausdorff, then we are here we getting two neighborhood ux and vx.
Yes.
So how can we get two neighborhood of x?
So tell me definition of Hausdorff.
Okay, sir. Now I understand. They tell that about two distinct points, but here is
Correct.
the single point.
Correct. So it has nothing to do with the Hausdorff length, right?
Yes, yes, sir. I
Okay.
understood, sir.
Yes. Now tell me that how to show that U intersection V must be empty. That means you have to assume that U intersection V contains at least one point, and from that you have to come up with some contradiction. Think about it. Take your time.
So can we say like this?
Yeah, continue, please.
Can we say like this? X belongs to intersection U A I and X belong to intersection V I. As there may exist some U A I which con- which is not which which intersection with Vi is empty.
Sorry, repeat one more time, please.
As for the as you have pictured the diagram, there may exist some neighborhood of X which intersection with the A is empty. So
Ah,
as
yes,
we are taking the
yes, but
complete
yes,
intersection
but is the what? But yes, that I understand. But what is that neighborhood?
intersection of whole complete UAI intersection VAI.
Ah, okay, X belongs to. So I mean, of course, U is. So of course, U is intersection of UAI, and V is union of VAI. Then then
So there may exist some UAI and VAI which does not contain X.
why? I mean, how? That's what the question is. Forget about picture. I mean, in mathematically, how to do that?
So I'm not getting that. How to write it?
See, the X belongs to intersection UAI, right? So that means what? X belongs to UAI for all I, correct?
So for all AI, uh,
Yes, for all AI. That's I mean the subscriptive AI. That's why I wrote in I.
uh,
And
yes,
X belongs to union VI. That means X belongs to VAJ for some J, correct? It is union. That is why for some. Is it clear?
yes, sir. Yes,
So that means what? X belongs to UAJ intersection VAJ. Is it clear? Correct?
yes, sir.
But their intersection has to be non-empty by construct. Their intersection has to be empty by construction, right? Because because how we chose those UAIs and VAIs, right? Where is those one? This is how we chose UA and VA to be empty, correct?
Yes,
So that is why the intersection must be empty. Is it clear?
yes, sir. As we there may exist some VIJ which does not contain X.
Huh?
So we are telling that X does not belong to UAIJ intersection VAIJ as some of VAIJ does not contain X.
Of course. But we are
That's why
getting
we are
by the construction. UA intersection of VA is always empty by the construction, right?
okay, sir.
So tell me, is the argument clear to you, crystal clear to you, or not yet? Or you may go through the argument once again, and then you tell that whether it is clear to you or not. Okay, take your time.
I understood, sir.
Is it clear? Is it clear? Is it clear to you? Is it clear to you?
Yes, sir.
Okay. The next question is, so next question is, basically this also show that what show that continuous image of compact set is compact. That means, so let f x to y be continuous, and if x compact, then f of x compact. Okay, so please try to do it.
Okay,
is
sir.
is the question clear to you?
Yes, sir. So I have to show the range of f is compact.
Yes, correct.
Sir, can we do like this? We just first of all we construct a open cover for the range space fx, and we took the inverse image of the that cover set. Yes, sir.
Yes, please continue.
We, sir, first of all we took the open cover for the range set fx, and we apply the continuity definition that the inverse image of open set is open, so we can conclude that the f is compact.
So we need to choose an open cover, right? So from where we're taking the open cover?
We are taking the open cover of y.
Okay, but you need to take an open cover of fx, right? I mean image of f, right? Not y, correct?
We,
We need to show image of f is compact, correct?
okay, so we can take the open cover
Of
mm,
image of f,
which contain the image effects.
correct, of course. Okay. So choose u open cover of f of x. Then
Sir, can we show like this as fx is compact, then x is compact?
As X is compact, then
As fx is compact, then x is compact.
that's what we need to show, na? If X is compact, then Fx is compact. This is what we need to show, right?
But we are, I'm thinking that like inverse, fx is compact, then x is compact in this institution as f is the continuous map.
No, no, no. This is not true. The question is that you have to show that X compact implies Fx is compact. I mean, this is the direction we need to show, right? That means we have to choose an open cover of Fx, and then we need to show that it admits a finite subcover. We are not. We are no need to show that Fx compact implies X compact. Correct?
At u is open cover, then f of fx, then can we write like this union u a1 u a2, the index family of open cover sets contain fx.
So U is an open cover of X if you choose. Then how from that how we are going to Fx? But F not necessarily preserves openness, right? Correct? I mean f of u not necessarily open. So is it clear? Is it correct?
I'm not getting this.
Okay, so I will explain in the next session. Today it's 2 hours and it's over. Okay, so on the next session I will explain this to you. Okay?
Okay, sir.
Okay. Bye.
Sir, hello.
Yes, yes, continue please.
Sir, I missed the first hour of the lecture. So
I will
where
upload the
can I?
I will upload the video in YouTube and so in the NPTEL log in NPTEL portal there will be a portion in the section called problem solving session
Yes, sir.
in the end of the list. So there you will click, it will go to an Excel sheet and it will give a YouTube link to
Yes, sir. There is a problem solving session available
you.
here.
Yes, correct, correct, correct. So there only I will upload those.
Okay, sir. Sir, you mentioned that the collect the note
Yes,
of
yes.
the faculty. So how can we get the
So
lecture note?
so you can directly email to NPTEL and they will send it to you.
Okay, sir.
Yeah. Okay. Bye.
That's it. Thank you, sir.